So these are the chapter 6 and 7 homework problems and solutions. There's some questions for each of them also. So for chapter 6, basically was talking about someone being launched by like a giant rubber band or something like that, or some sort of ride, and in a box, which is kind of creepy. But essentially, as soon as the person is launched, they're in free fall, so their weight would be 0. And in this case, question 13 was a hand pushing down on a book, which is resting on a table. So the normal force of the book has to be larger than mg of the book, since both the hand and gravity cause forces down, so the normal force is the only thing acting up. Problem 31, actually I'm going to go through, scroll through the problem so you can fruit fly. Look at those if you want. And talk about them as we go. It's number 9 in chapter 27, or 7, problem 18. Problem 27. Problem 28 and 35. 35 is a good one, by the way. Problem 46. Obviously, I screwed up here with, I think I thought it was 70 kilograms instead of 80, so I had to mess around and get that. All right. Going back up here, I'm going to go through and solve some of these particular problems. That was Mrs. Osment. I just told her to be quiet. At any rate, you've got an elevator. It's accelerating initially. It goes at constant speed and then accelerates again when slowing down. So since we know an elevator would have to speed up at first, and the graph showed the weight going down, the motion would have to be downward. mg would be greater than the normal force up. So for letter B, finding the person's mass, I use G for most of my problems for this as 10 newtons per kilograms. So the large stretch where the elevators, where the person's force was 750 newtons, that was 75 kilograms. So to find the distance, this was actually quite challenging. I had to use the force and the person's mass to figure out the acceleration. So initially, using the formula F equals mg plus a, the 600 newtons meant that the acceleration was 2 meters per second squared downward. So figuring out how far that elevator travels during those first 2 seconds would be 4 meters. Then I can use a times t to figure out how fast the elevator is going at the end of those 2 seconds, and that was 4 meters per second. So at a constant speed, moving from 2 to 10 seconds, that means the elevator goes another 32 meters. And then finally, the displacement during the third part, when it's slowing down, has an acceleration of negative 2 meters per second squared, but an initial velocity of 4 meters per second. It travels another 4 meters. So overall, the displacement of the elevator is 40 meters. I guess I did not need the mass to figure that out for any of those. But that was pretty challenging. For 33, I like this problem. It's actually pretty cool. It shows how medical people have to use physics as well. The key thing is thinking about the different points. This point where the foot is attached is key in my mind. So for part A, to find the tension, you simply realize that the tension in all parts of this string is going to be the same if it's a light string. So we'd look at this part and this system to think about that. So if I use 10, again, newtons per kilogram, that would be 60 newtons. If you use 9.8, it would be 58.8 newtons, and the rest of your answers would be slightly different as well. So to pull straight out on the foot, which is what this traction is meant to do, we know that the force up has to equal the force down. Well, the force down is the mass of the foot or leg multiplied by gravity's gravitational field strength, and then the component of this tension pulling down. The force upward is the component of this tension pulling up. So we know that pulling down, we've got 40 newtons caused by the weight of the foot or leg, 60 sine of 15 degrees caused by the vertical component of this string. That's 55.5 newtons down. So since we also need that force up, that's how we can go back and figure out the angle, which is a 68-degree angle. So I didn't draw this very well. It should be much more vertical. For part C, to find the tension or the traction force, that's simply the horizontal components of these things. So if I know that this is 60 newtons and that's 60 newtons, simply 60 newtons times the cosine of this angle, which was 68 degrees, plus 60 newtons times the cosine of this angle, which is 15 degrees, and that will give me my traction force. And that was around 81 newtons. For problem 35, it gave me an acceleration, a position function. So to figure out the net force at the different times of 0 second and 1 second, I need to find the acceleration function. So I take the second derivative of position, so take the velocity derivative, and then the acceleration is the derivative of velocity. Technically, I think you could put d2p over dt squared or something like that. And so that gets me this equation. So when I plug in 0 seconds, I get negative 6 meters per second squared, and therefore negative 12 newtons. At positive 1 second, I get 6 meters per second squared, so positive 12 newtons. For problem 55, I've got something acting on a wall. I've got a force pushing with 12 newtons at a 30-degree angle from horizontal. So I can figure the force upward caused by that would be 6 newtons. The force downward caused by gravity acting on this book is 9.8 newtons. So there's a net force down, not including friction. To find the force of friction, I need to find the normal force of this block into the wall. So that would be the cosine of this angle, which is 10.39 newtons, multiplied by the coefficient of friction. And really, this should be a less than or equal sign. So I did not remember to do that. I guess I put it up here. So essentially, the coefficient of friction of wood on wood is less than or equal to 0.5 for static friction. And so the static friction between these two surfaces can be as high as 5.2 newtons. Here, the box won't move because this difference is only 3.8 newtons, but friction can be as much as 5.2 newtons. In this particular case, friction actually would be acting upward since that's the lower force of these two vertical forces. Chapter 7, these are the conceptual questions. We'll probably go over those. Tug of war is kind of interesting. It involves other forces interacting with the ground. This is just a fun question because it's ridiculous. But basically, you think of that as a whole system. And so the magnetic forces are interactive. It's kind of the same reason a tension force on a rope would not accelerate the system because tension is acting in both directions. And then here the tension in the scale would read 5 kilograms. It has to, otherwise at any particular point, these would be accelerating. So problem 9, 1,000 kilogram car pushing a 2,000 kilogram truck. Not much to say about that. 18 was pretty useful. The picture was kind of nice with a little cat and a dog there. So I thought about points A and B, which I've labeled as points of interest. So at both of those points, the objects have to be in equilibrium. So the right component of basically tension 2 is equal to the leftward component of tension 1. The upward component of tension 1 is equal to 20 newtons down. And once again, I'm using 10 newtons per kilogram in here. Okay. So I told you theta 1 was 20 degrees. So at this point, I know if it's 20 degrees, and I've got 20 newtons down. I need 20 newtons up. That means T1 is equal to 58.5 newtons. So the horizontal component of this would equal T2. Point B, I know that the horizontal component, which is basically all of T2 to the left, would equal T3 to the right. And I also know that 40 newtons down would equal T3 up. So I can set those two equations equal to each other to find the angle. Now, actually, I think Zach Wisenbach in class asked me, well, could I do it this way? And think about just that that's the horizontal force and that's the vertical force. Yes, I could have done that much more simply. So I ended up doing it as a term of ratios, so that 55 over the cosine of theta 3, or basically the horizontal, or this was a horizontal equation, this was a vertical equation, set those equal to each other, cross multiply and I get tangent of angle 3 is 40 over 55. Well, I could have done that a lot simpler. So this is a 36-degree angle up here. And then if I know it's a 36-degree angle, I can just plug in to either one of those equations that I used earlier and get T3. 27 I like because it's a Star Trek one. Essentially, you've got a big starship with a tractor beam on a smaller shuttlecraft. The accelerations are proportional, or inversely proportional to the masses. So the shuttle has 1/100th the mass, so it has 100 times the acceleration. The net acceleration between the two is 2.02 meters per second squared. I can use that to figure out the time it would take the tractor beam to bring the shuttlecraft in. And I can use that multiplied by the acceleration of the large starship to figure out how far it is pulled. So tractor beam would definitely pull on both objects. P28. Ooh, this is the one with the cheekbone in the forehead. I'll let that go. Problem 35 is actually a really good problem. Hopefully we go over that in class. All these things have a coefficient of friction of 0.3. The lower block and the upper block, and the lower block of the surface. So the key thing here that makes this sneaky is with this pulley, basically the top block is being pulled to the left, the bottom block is being pulled to the right. I've got 20 newtons of external force. So I need to figure out, to find acceleration of this system, I could do F net over M tote, but there's a lot of friction involved. So the first thing I want to think about is the friction of the bottom block on the top block. In other words, they're rubbing each other. So that's due to the normal force, which would be 10 newtons. Actually, I think here I use 9.8 for some reason. So 9.8 newtons per kilogram times 1 kilogram times 0.3. So that says that this normal force is 2.94 newtons. Or pardon me, the normal force is 9.8 newtons. The friction force is 2.94 newtons. So essentially, this bottom block is acting against the top block with 2.94 newtons of friction. But because of interactive force pairs, this top block isn't just interacting with the ground, it's also interacting on the bottom block. And it is opposing the bottom block's motion with 2.94 newtons. Okay. And then the friction of this big block here, the bottom block on the surface, we use the normal force of that. Well, that's basically going to be almost 30 newtons because we've got 3 kilograms resting on the surface, and multiply that by 0.3. So although I've only got 2 blocks, I actually have 3 forces of friction opposing motion. So 20 minus 2.94 minus 2.94 minus 8.82 all over 3 kilograms. That's what gives me my answer. I like that problem a lot. It is sneaky. This last one is something called a Bosun's chair. We can go through that conceptually as well. I think the key thing is drawing a Freebody diagram for the person in the chair. So we know that gravity is acting down. I had initially thought it was 70 kilograms, but actually it's 80 total kilograms, so that's mg. And there's 2 forces upward. So the rope is pulling on the person's hand here. The rope is also pulling on the chair here. So that means that the rope only has to be about half as much force as mg down. In fact, it would have to be exactly half as much if this person were at rest. But it said they're accelerating upwards at 0.2 meters per second squared. So we need 40 newtons of net force upward. So I could say 2F upward minus mg downward is equal to this 40 newtons of net force upward. which I think I kind of just rewrote here as being 80 times 0.2. Should have just had that as 40 newtons. So that comes out to be where 2F, twice the force of or tension in the rope, is 824 newtons. So the force of the rope would have to be 412. Kind of a cool example. At any rate, that's a lot of talking. Hopefully you go over those. Thanks.